The activity you guys are going to be doing today is actually going to be for your formal lab. So we'll talk a little bit about lab write-up and what it should include with this. You guys will have a formal lab write-up, probably 1 to 2 per marking period. The other labs that you see will be more like packet labs. Here's your activity, do it, collect your data, and give us conclusions, maybe graphs and stuff, but nothing that has to be formal like you will see with this chromatography activity. So underwater still, you guys are opening up chromatography with a flare, and it's going to tell you a little bit about chromatography. And if you break down the word chromatography, you guys should realize that chromo means color. So what you guys are doing today is basically something called color writing. And it's going to involve words like solute and solvent and solution and things like that that we've been talking about within your water notes. So we know that water is a universal solvent. You guys are actually utilizing water today. And we're going to use what is known as chromatography paper, which is looks like white paper, but it actually is very porous, which means that it has openings in it so things are able to travel. It's almost like a coffee filter. And you could buy it with different pore sizes in it, depending upon how fast you want things to move. We're also going to use little vials. So the little vial, you guys are going to notice it's got that black magic marker line across the bottom. It's going to tell you within your activity to mark 1 centimeter from the bottom. So these have already been marked for you, so it's 1 centimeter from the bottom. And what we're going to do with that is we want to take some water and we want to fill water up to that 1 centimeter line. So just a little bit of water, centimeters worth of water within that. We'll put that nice and flat. And we really don't want to touch that once we introduce our chromatography paper to it. Your chromatography paper, we don't want to go touching it too much and getting oils all over, because remember, we want things to run through it. But on that paper, you want to measure 2 centimeters from the bottom, and we want to put a mark there because that's the mark where we're going to create our origin, or where these colors are basically going to start from. So there's my pencil mark, and I want to do it in pencil, as you guys will see a little bit later on in this lab. And on that, we're going to go through and I'm going to put a black dot right on that pencil mark. So I'm going to kind of let that dry a little bit. I don't need a giant dot. Let it dry, and maybe I'll just do it just a little bit more. So here's your problem that you guys are going to be creating a hypothesis for in a moment. So your problem is what's going to happen to that black dot that's on that chromatography paper when introduced to your solvent, which in this case is water. So this paper is actually going to be slipped inside there. It's going to hang out for a little bit. What's going to happen to that black dot and why? So the black dot will do blah, blah, blah because blah, blah, blah. Tell me why. Must give me a reason why. Think about water terms, universal solvents, things like that. Make sure it's bold. No, I think. No, I believe. This hypothesis is an educated guess. It does not have to be right. So once you get done this lab or this activity, please don't go, oh, that was completely wrong. Go back and erase it and change it. I don't care if it's wrong as long as it's bold. It's your educated guess based on things that you have learned previously. Okay, so take a few moments now. You can pause this video, do a little hypothesis. If you are those virtual groups, I might ask you to kind of send them to me on the little chat in the Google Classroom. Okay, once that hypothesis has been approved, you guys are going to go through. We are putting this or introducing this chromatography paper into the water. And it's a little harder to see because of the colors here. Let me see if I can get something a little dark behind there for you guys. But what you should start to see is that the water is being pulled up against gravity on that piece of chromatography paper. It's just about to hit the line right now, and it is hitting the dot and being pulled up. So if you remember that term within our water notes, that term is called capillary action. So this capillary action is caused by different characteristics of water because water is polar covalent. Remember we talked about cohesion and adhesion. So those little water molecules are clinging together and they're forcing each other up. That's capillary action. They're also sticking to the paper, which is adhesion. Water sticking to non-like substances. So this cohesion and adhesion, we see capillary action being pulled up against gravity. And right now that water is moving through and it's combining with that little dot. And what you're going to see is that black little dot is going to start to change. So my pencil mark that you guys see here, that's known as my origin. This is where my colors started from. So you go, well, black is in a color. Well, we do have colors that you guys are going to start to see breaking apart from this. And it looks like the dot is starting to kind of get larger. But what's happening is that little black dot, my solute, is being broken down into a solution. And that solution is what's being pulled up against gravity. And what we're going to see here is that things are going to start to spread apart. Things are going to start moving. So it's important to remember that things move based on a few things that you'll see within the notes. So first off, it's going to be based upon molecular mass. Heavier objects, or colors, let's say, are going to stay closer to the origin. Your lighter colors, and I don't mean like pink and yellow, I mean like in terms of molecular mass, are going to travel farther away from the origin and move their way up the chromatography paper. So besides molecular mass, we also have solubility. How easily can these things be dissolved? So we're going to let that go. We're going to let that go. It's kind of like the little cooking shows. We'll pull one away. We'll put the other one in. We'll say, oh, a couple minutes later, this is kind of what we have and where we are right now. And as we keep going, some of the things that you guys are going to see is that, yes, you're going to get color movement and things are going to start to break out. The very top of that water, where that water is in the line, and you guys can start to see them at the very top here, that's known as a solvent front. So it's just starting to move. You guys can see water, right about there if you look closely at it, and you'll see it on the final product here in a moment. But what you're noticing is that black dot is no longer on the origin. It's moving up. My water's still down here, but what's happening is it hit the black dot, went into a solution. The solution's getting pulled up against gravity and moving on. So now my final paper looks like this. This was my origin. Water got pulled up and it moved up. All the way at the top up here, this line that I drew, this is the line where the paper was dry and where the paper was wet. This line is known as your solvent front. This is important because that's going to be one of your measurements that you guys are going to utilize in order to calculate out your RF values, or retention factors, that we're going to see. So you guys will be utilizing rulers. We want to stick that ruler. We're going to utilize centimeters, and we're going to put that 0 mark right on our origin, because it's important to remember all of our colors started from the origin. And you want to use your observation skills. We want to look at our qualitative data now. We want to look at colors here. And from that black dot, you want to start breaking down colors. And I could say, and everybody might see a little bit different color. On the pictures that I'm sending you guys, you have to kind of expand them open, look at them real closely. I can see pink. Pink is starting right about here, and I'm going to say it probably ends right about there. Does some of it scoot up the side a little bit? Sure. Use your best judgment. Do you want to measure where most of the color ends, all the color ends? It doesn't matter to me, just be consistent. After pink, you guys are going to see you have a little bit of yellow in here. So it's important to remember, yellow did not start moving where pink ended. Everything started from here. So when I measure my pink color, I'm measuring from the origin up to about here. So I might say it's about 2.2 centimeters. Yellow, on the other hand, started at the origin again, and we're going to say it went to about 4.5 centimeters. I've got some blue. I have another pink up here. This pink is definitely different than the pink that I see here. So maybe it's a lighter pink. It's definitely lighter in terms of molecular mass. It traveled farther from the origin. The other measurement that I need to make sure I'm marking down is my solvent front. In the solvent front, I would say on mine is about 7.3 centimeters. Yours might be different. I need to utilize those. Those of you guys who are in class need to take a photo of your particular chromatography paper. It will become part of it, and you may want to do a little sheet like this, of course a little nicer and neater than what you see of mine, and let me know how far each color moved. This eventually is going to be going into a data chart for you. So I can say, oh, here are my colors. I have pink, yellow, blue, and light pink. And then I can put my measurements. They traveled 2.2 centimeters, 4.5 centimeters, 5.2, 6.8, whatever it may be. And then your third column is going to be what is known as your RF value. So your formula for your RF value is the distance each color moved and that's going to be in centimeters, and that's going to be divided by the distance of your solvent front. That's also in centimeters. So what you guys are going to notice is as you guys go through these calculations, the units are going to cross each other out, and you're not going to have any units on your RF values. Your number on the bottom is going to stay the same for all your calculations. So I want to know, what's my RF or retention factor for pink? 2.2 divided by 7.3. Nothing should be larger than 1. Everything's going to be a decimal point. You guys should take them to 3 places over. Okay, so 3 places within the decimal point. Nothing should be larger than 1 because nothing traveled farther than that solvent front. The pink's getting kind of close to it, but it definitely didn't travel farther than the solvent front. So then third column of your chart, you guys are going to go through and create a column for a retention factor. Yes, we need to see all your calculations. I want to see this formula. I want to see how you found the pink RF value. Put the numbers in there, show me. Show me for yellow, show me for blue, show me for light pink. Somewhere near that data chart, you should tell me what the distance of that solvent front is, because that's always going to be your bottom number. This will be included within it, and then you guys are going to graph this information. So now that you have that data chart, you're going to graph it. So you're going to graph those colors as well as, and you can do it one of 2 ways. It's completely up to you. Centimeters, probably the best way to do it is your retention factor or your RF value, since that's what we're kind of calculating out. And then you guys will make a conclusion from there, and we'll talk about the conclusion a little bit more with our class notes on that.